everybody. My name is Sebastiano Fichera, and I'm a PhD student at Ventura. And today we'll talk about two elements in the context of XFAM, and the handling of double discontinuities still in two-definite elements. So, as you know, XFAM is pretty useful in fractal mechanics because it allows us to avoid progressive remeshing and still being able to evaluate the behavior of a structural element, of a cracked structural element. This is done by enriching the elements cut by the discontinuity. The enrichment is done by adding to the solution space an enrichment function that is a discontinuous function that reproduces the behavior of the displacement field. So the nature of the discontinuous function depends on the nature of the discontinuity itself. For strong discontinuities, so cracks, we use a heaviside step function. This is the good part of XFAM. The other side, on the other hand, we have that using all this discontinuous function, when it comes to integrate, for example, when we have to find the stiffness matrix of an element, all the terms that contains a discontinuous function are not integrable using standard quadrature rules. So we have to do some tricks, for example, divide the element into subdomains along the discontinuities, so we can evaluate the solution and the integral in a domain where the discontinuous function is somehow continuous. But of course, this means this is some kind of remeshing, if we want. So a solution was proposed by Professor Ventura from Polytechnic Torino by the means of equivalent polynomials. What does it mean? So instead of dividing the element and have to track the boundaries of each part, each subdomain, we can find an equivalent polynomial function, so h tilde there, that is found so that the integral over the entire domain of the equivalent polynomial times the polynomial function, a generic polynomial function, is exactly equal to the sum of the integral of the discontinuous function times the same polynomial function on the left side, integrated first on the left side of the domain and then on the other side of the domain. So if this polynomial function exists, is it possible to integrate and find, for example, the stiffness matrix of an element without splitting the element? So you can integrate on the entire element, on the entire domain. So we started from that, and we use this technique to find a polynomial function that is usable when we have more than one discontinuities. For example, with two discontinuities, this is a case that can be, for example, in real life when we have a branching discontinuity, a branching crack, or even a kinking crack. So what we did was to, for example, take a square element, simple square element. Imagine that the cracks are these two lines, R and Q. And so we found equivalent polynomial h tilde, so that the integral over the entire square element of this function, so a generic polynomial function times these equivalent polynomials, is equal to the integral of the same polynomial function p over just one of each one of these subdomains. So in other words, we integrate, we don't define the boundaries of each one of these subdomains, but we're able to integrate over each one of the boundaries without defining exactly where the integration domain is. So we did this very rapidly, starting from the Professor Ventura formulation. We made a position, so we set a boundary of integration that corresponds to the intersection point of the two discontinuities. And the difference in the solution of the polynomial function found for just taking into account one discontinuity, so the two discontinuity, then the polynomial function found taking into account the other discontinuity. The difference between these two solutions gave us in this case, the A part of the domain. So we have a closed form solution depending just on the parameters of these two lines. So you draw the lines using the ABC parameter in the Cartesian plane, and that's it. You can find this part of the subdomain, and the other parts, so B, C, and D, are you can simply find them just solving a simple linear system. So the key part is just to find one of these four, and then you can find the other three. Of course, all of this was put into a library written Fortran code that could be useful not just on the engineering and structural point of view, but also to solve mathematical problems stated like this one. And this library contains just not the square element, but also various 2D and 3D domain of integration. So there are a lot of things that one can play with. We also did a numerical test of this. This is the example we saw previously. So here, basically, we inputted in the program, in the library, just the position of these two lines. We say to the library that we were integrating in using a square domain, and integrating over the entire square domain. So without defining the boundary of A, B, C, D, we were able to find, for example, the geometric properties of each one of these parts. And if you can see, there are also subdomains with an interesting shape that is not so easy to reproduce directly analytically. After that, we move also to software implementation of the shell elements still in the external context. This is a work made in collaboration with the STS software house, an Italian software house based in Sicily. Basically, still very rapidly because it will take so much time. 4-node and 3-node shell element with sperm classic formulation were implemented into the framework competencies. It is a pretty widespread framework, pretty used, of course, for earthquake engineering. And we use these two elements. This is a pretty new work, so for the moment, we use these two elements to reproduce, you see an example, a validation example of a cantilever beam with an existing crack that was modeled first using the proposed XFEM formulation, and then using the standard FEM formulation. So here we subdivided the elements so that the finite element nodes will follow the exactly the correct position. And we found that the results were identical. So after we were able to validate this, we went straight on to an example where the element is not damaged. So we applied the same forces as before, and we saw what happened, so how the element would behave, and we saw that there is a generation of progressive tracking for each step, this progressive law, when until the lability is finally reached, so the analysis can proceed. Same thing we did the same thing with an inch beam. Here we have actually had two cracks generated in the bottom that develops the same way, like mirrored, until still lability is reached. This may be due to the thick discretization of the element. Maybe we still have many things to try on this particular cases. So this is our work. This is going on right now, and that's it. Yeah.
Okay, thank you. Any question? No question in the audience. So you mentioned you can go 3D with this formulation. But
Yes, we
the
can.
geometry in 3D is much more complicated than in 2D. So you have to split not only in four subparts, but
actually we found also a closed form solution for the 3D case, just for the hexahedral domain shape, so a cube or subspecies of a cube. And yes, the thing is a little more complicated because, as you said, you have also the Z dimension to deal with, but still imposing this position, so using let's say a moving integration boundary. So we use this S thing here. In 3D, we don't have anymore a line. We of course have a plane that can be that can have a slope that varies on the plane. So we fix the position where the S 3D plane has to have a zero Y component, and using that, integrating like that, basically it's the same thing in 3 dimensions. We were able to find a closed form solution. So yes, you can totally use it also in a 3D case. So,
yeah, and back in 2D, when A or D goes to 0, you don't have any numerical trouble. Hill conditioning.
If one of this is parallel to the
the green line could be parallel to the purple line,
you say if
or the area A goes to 0.
Okay, so actually, when the intersection point is within the element, you have to use this solution to find one of these 4 parts to solve a linear system that make you find the remaining parts. If this intersectional point is on the boundary, or outside, or to the infinity, basically you can write a linear system to find the 1, 2, or 3 parts in which the element is split, but they are not linearly dependent on each other. So you can use the formulation, the classic formulation, the one presented by Professor Ventura. This one, without the need of subtract from one to another of course, in the library, all these cases are handled by exceptions, or by many exceptions. So yes, in other words, this point can be wherever, anywhere, and you can find anywhere solution. So it's secure.
Okay.
Pretty solid.
Any other question? No, then. Oh, yeah. Sorry.
I would like to ask, like, what do you mean by double discontinuity? Are they both simultaneously?
Are they same?
Are they in the same elements simultaneously?
Yes, of course. Like if you have, for example, a crack that is branching at a certain point. So if you mesh it, it can happen that this double discontinuity, that you have two cracks in the same finite element. So imagine that you don't see this part. This is a straight line that goes like that. So you can handle, or maybe
but then they don't intersect, right?
Yes, of course they intersect.
Not the way it is. Like really going forward. If they branch, they are different.
They have an intersection, a generating intersection point from which they branch. Or even if a crack is kinking, so it changes its slope, it's pretty much the same thing. So imagine that this part doesn't exist, and you have a crack that changes its slope. So it can be applied in many cases. You just have to imagine it and adapt it to your problem in real life.
Okay.
Okay.
Thank you.
So let's thank again.